Hello and welcome to lecture 49 of the course Computational Complexity. In the previous lecture, we saw the complexity of unique set. We saw that even when restricted to the case when the given Boolean formula has 0 or 1 satisfying assignment, the problem of determining which of these is the case remains hard. So now in this lecture, we will see a related problem. So given a satisfying assignment, given a Boolean formula, can we count how many satisfying assignments this Boolean formula has? Right? So it could be 1, it could be 10, it could be 100, or it could be 0. Now, if we could do that, how powerful is this? So counting in general, or given a graph, can we count how many cliques it has of a certain size? Given a graph, can we count how many cycles it has, right? So counting the number of objects of a certain type is a problem that we will look at, and we will try to understand the complexity of this counting, right? So to begin, we will first define the functional equivalent of P, right? So till now, everything that we have seen are decision problems, right? Given a language, is a given string is in the language or not in the language. And similarly for promise problems, right? Given a yes class and a no class, is a given string in the yes class or the no class. So this is all yes no questions. But the counting problems are not yes no questions, because we have to, the answer is the count. So we first define what is called FP, which is a functional equivalent of P. FP consists of all the functions that can be computed by a deterministic polynomial time Turing machine. Okay, that is FP. So here I have written the definition formally, and Sharpie is a complexity class that captures the power of counting. So Sharpie corresponds to all the functions which can be captured by the number of accepting computations of a non-deterministic polynomial time Turing machine. Okay, so fx, so Sharpie contains all the functions such that fx is the number of accepting computations on an input x of a non-deterministic polynomial time Turing machine. So this may seem abstract. Just to make things simpler, so consider sharp set. So given a Boolean formula phi, how many satisfying assignments does this Boolean formula have? Right? So satisfiability is in NP, right? We have seen it is an NP. And how did we show that it is an NP? We use the guess and verify model. So we would guess an assignment and check whether it is satisfiable. So potentially we could guess all the 2 power n assignments, where n is the number of variables, right? And so how many of these assignments will lead to accept? Well, if it has 10 satisfying assignments, all these 10 satisfying assignments will lead to it getting accepted. If it had one satisfying assignment only, then it would only have one satisfying, one path that leads to acceptance. So one simple example of a language that is in Sharpie is sharp sat, or in other words, which is I have written here, it is the number of satisfying assignments of a given Boolean formula phi, right? Because sat is clearly in NP, and the number of accepting computations is merely the number of satisfying assignments. Another example is 3 coloring. So given a graph, how many 3 colorings does it have? So 3 coloring is in NP. Again, we had a guess and verify model to show that it is an NP. We would guess a 3 color assignment that uses 3 colors, and then we would check whether this assignment is a proper 3 coloring, right? So the number of accepting computations is merely the number of proper 3 colorings of the graph. So again, 3 coloring is in Sharpie. So 3 coloring. So again, these are all examples in Sharpie, so I am not explicitly writing these are all in Sharpie, right? So we have a problem in NP, and we look at the counting version. So just to give another definition, we could use the verifier model of NP to write the definition, right? So I first said that it is a number of accepting computations. So in the verifier model, instead of a non-deterministic Turing machine, we have a deterministic Turing machine, right? The verifier. I think in the lecture we use the symbol V for that when we defined the verifier model. So maybe I'll just stick to that. So where X is the input and Y is the proof or certificate. So now we are just counting. We are asking because there is no non-determinism in the verifier. Verifier is deterministic. So all the non-determinism gets pushed into the choice of the proof or the witness certificate, or rather by that I mean the choice of the proof or certificate, right? So how many Y's are there that leads to the acceptance of X in V, right? So that is another way to characterize sharp P. So given, so what is sharp P? It's a class of all functions which map X to the count. So it's X is from 0, 1 star to a count. Count is a natural number, of course, and where the function corresponds to the number of Y that leads to X being that leads to X being accepted. So Fx is the number of distinct Y for which X is verified correctly. So the number of proof or certificate strings for an X. Okay. So sharp P also enumerates the number of accepting paths. Again, this is just a repetition. So we saw two examples. One is sharp sat, right, which is in sharp P, and then sharp 3 coloring is in sharp P. Right. So maybe I'll just write that here. Sharp sat is in sharp P, and sharp 3 coloring also is in sharp P. So one may ask, is it the case that what about other, like, both sat and 3 coloring are in NP, but we could also have problems in P, right? So for instance, bipartite perfect matchings. As I had mentioned before, given a bipartite graph G, to decide whether it has a perfect matching or not, it has a polynomial time algorithm. So now I can ask, what is the number of perfect matchings in this graph, right? So this is in sharp P. Sorry, not P but sharp P. And I could ask another question, given a graph G, right? What is the number of spanning trees of G, right? Again, this is also in sharp P. So one thing to note is that the first two problems, sharp sat and sharp 3 coloring, these correspond to the, so 3 coloring and sat are both NP complete, right? Even though they are in NP, they are NP complete. So sharp, even the counting version is hard. Even though the counting version sharp 3 coloring and sharp sat are both in sharp P, the counting versions are considered hard. And even for the case of bipartite perfect matchings, even though we think that bipartite perfect matching, the decision version is easy, right? There are efficient polynomial time algorithms. The counting version becomes hard. Okay, so this is so just to summarize, maybe I will just make some space here. Not to summarize, maybe I'll just say note or remark. Sharp sat, sharp 3 colorings, sharp bipartite perfect matchings, all are hard, meaning we don't know of an efficient way of doing this, and we believe these are all hard. Later we will see sharp P completeness, and in fact all three of them are sharp P complete. But sharp spanning trees is actually in FP, which means it can be, there is a deterministic polynomial time algorithm to compute this. So basically it boils down to a determinant computation, right? So some problems, even though the decision version is easy, the counting version becomes hard. But not all problems need to behave like that. Like spanning trees and bipartite perfect matching, the decision versions are easy. But spanning trees, the counting version remains to be easy. But for bipartite perfect matchings, the counting version becomes hard. Right? Okay. Some observations is that Sharpie seems to be more powerful than NP, or at least as powerful as NP. Right? More, or at least as powerful as NP. Well, why? In NP, let's say satisfiability, the goal is to determine whether this formula has a satisfying assignment. So if we can count the number of satisfying assignments, we can check whether the number of satisfying assignments is 0 or more than 0. Right? So if we can count, we can certainly decide whether it is satisfiable or not. If we can count the number of proper 3 colorings, we can certainly decide whether the number of proper 3 colorings is 0 or something greater than 0, right? So if we can, Sharpie is at least as powerful as NP. And similarly, Sharpie is at least as powerful as the randomized classes RP, BPP, etc. Right? Because we can again view the randomized Turing machines as deterministic Turing machines, which takes the random string as an extra input. Right? We can view it as a deterministic Turing machine that takes the input and the random string. And we can view it like how many random strings allow an input x to get accepted, or how many random strings lead to an input string x getting accepted. So that can be done using Sharpie. Okay. And once you do that, now you can count the fraction of random strings, random choices which lead to an input string x getting accepted. So if you want to check whether a given input string is in the language, we just check what is a fraction or what is the probability by which it gets accepted. So for which we can estimate we can estimate by the number of accepting or number of fraction of random strings that lead to it getting accepted. So you can check if it is if it is a BPP machine, then we can check whether the fraction of accepting strings is greater than 2/3 or less than 1/3. If it is RP, we can do the corresponding thing, right? If it is in PP, then again we can do the corresponding thing. So if we can count the number of accepting computations, we can also decide the probabilistic polynomial time classes RP, BPP, etc. Right? So the point is P is at least as powerful as all these classes, right? And yeah, so this is another point. And the next point is something that I have already made. In the case of sharp SAT and sharp 3 coloring, these correspond to NP complete languages, or the decision versions of which are NP complete. If we can count the number of accepting parts in polynomial time, if sharp SAT is in if we can count the number of satisfying assignments in polynomial time, right? If sharp SAT is in FP, right, then it means that we can even decide whether it is satisfiable or not in polynomial time, which means P equal to NP. And same thing holds for 3 coloring as well. If we can count the number of proper 3 colorings, we can decide whether it's 3 colorable or not, which means P, because 3 coloring is NP complete, this would imply P equal to NP. So these two problems, we have the decision version is hard, so the counting version remains to be hard. And as I mentioned earlier, like I already illustrated one bipartite perfect matching. Now we will see another problem, which is just counting the number of cycles. So to decide whether the graph has a cycle can be done in deterministic polynomial time, right? Now we are saying that if we have an algorithm that counts the number of cycles, right, in polynomial time, then P equal to NP, right? So the counting the number of cycles implies P equal to NP, right? So Decision version is easy because it's easy to decide whether the graph has a cycle, but counting version is as hard as NP complete, right? So let's see why this is the case. So the formal statement is, if counting, so I am using sharp cycle to denote the problem of, so the problem of estimating the number or counting the number of cycles in the graph, right? So these are labeled cycles. So each cycle, each label is counted separately. Okay. So if the number of cycle is in Fp, which means if we can count the number of cycles in polynomial time, Fp is just the functional equivalent of P, then we will it will imply that Hamiltonian cycle is in P. So as we have seen when we saw NP completeness, Hamiltonian cycle is an NP complete language. So if Hamiltonian cycle is in P, that implies that P equal to NP. So let us see why this is the case. So the main idea is, we will use a gadget where we replace, so given graph G, we want to count the number of cycles of G, right? So what we will do is replace each edge of G with a gadget such that any cycle in G becomes a lot of cycles in G prime. So we'll transform G to G prime using this gadget. So any cycle in G becomes a lot of cycles in G prime. And the bigger the cycle, the more cycles are produced in G prime, right? So Hamiltonian cycle is the biggest possible cycle that we could have in G. So that results in a lot of cycles in G prime. And in fact, the only way that we will have so many cycles in G prime is if G had a Hamiltonian cycle. So that will give us the equivalence. So the gadget is really simple. Any edge, the edge is in the left hand side here, UV is replaced by this crisscross network. So you can see that UV is just one edge in G, right? So this is G, and in G prime, corresponding to UV, we have 2 power m paths. So from U we can go up, then go down, then up. So every stage here, 1, 2, 3 up to m, you can decide to go to whichever level you want, the top level or the bottom level. So there are 2 power m choices to go from U to V, right? 2 power m choices in G prime. And now suppose you see, let's say you have a cycle A, B, C, D in G, okay, a 4 cycle. How many cycles does it correspond to in G prime? Well, the edge AB will be replaced by a similar crisscross network. So there will be 2 power m paths from A to B, 2 power m paths from B to C, 2 power m from C to D, and 2 power m from D to A. So there will be 2 power m paths for each edge, right? And you could choose for each of these edges, A, B, B, C, C, D, D, A. There are 2 power m choices. 2 power m whole power 4 is the number of cycles that we have in G prime corresponding to this cycle in G, this 4 cycle in G. 2 power m whole power 4, which is simply 2 power 4m. So in general, if we have a cycle of length k, this leads to 2 power km cycles in G prime. So a cycle of length k in G leads to a cycle of length 2 power km in G prime. So now we will come to the main statement or main key point. Right? So we will say that, so again, till now I have not mentioned what should be m. So whatever m is, we have some corresponding relations. So if m is large enough, let's say m is n squared, then the claim is that if G has a Hamiltonian cycle, if and only if G prime has at least 2 power n cubed many cycles. So G has a Hamiltonian cycle if and only if G prime has at least 2 power n cubed cycles. So one direction is really easy. Suppose G has a Hamiltonian cycle, right? That means it's a cycle of length n, right? So Hamiltonian cycle means cycle of length n. Now G prime has 2 power m multiplied by n cycles, right? So the same thing, 2 power 4m that we did above. Similarly, 2 power m multiplied by n, because where n is the length of the Hamiltonian cycle, and by our choice of m is also n squared. So m times n is n cubed. So Hamiltonian cycle leads to 2 power n cubed corresponding cycles in G prime. Okay, 2 power n cubed corresponding cycles. Now suppose G does not have a Hamiltonian cycle. Now we want to say that G prime does not have 2 power n cubed cycles, right? And that is also not very difficult to see. Any cycle in G prime correspond to some cycle in G, right? Because the only thing we are doing is replacing an edge with some mesh network. So if there is a cycle in G prime, there is a cycle in G, or in a, yeah. So if G does not have a Hamiltonian cycle, the largest cycle in, so you look at G prime, let's say you want to check the number of cycles. So instead of counting the number of cycles in G prime, what we will do is to count the number of cycles in G and see how many corresponding cycles it gave rise to in G prime. So what is the largest cycle in G? What is the length of the largest cycle in G? We know that there is no Hamiltonian cycle. So the length of the largest cycle in G is n minus 1. Right? So the length of the largest cycle in G is n minus 1. How many cycles could have been there in G? Right? So the first vertex can be chosen in n ways, second vertex could be chosen in n ways. In fact, you cannot repeat a vertex, but anyway, we are considering an upper bound. So there are n power n minus 1 ways to choose a cycle of length n minus 1 or smaller in G. So this is an upper bound, n power n minus 1, right? This many ways are there to choose a cycle in G, at most this many ways. And so these are the number of cycles in G, or there is an upper bound on the number of cycles in G, n power n minus 1, and each cycle is of length at most n minus 1. And we know that each cycle of length n minus 1 gets blown up into 2 power n minus 1 into m cycles, right? Because each cycle of length m corresponds to 2 power m into each cycle of length k corresponds to 2 power mk cycles in G prime. So the number of cycles in G prime is the number of cycles in G, which is n power n minus 1, into or multiplied by the number of cycles that each cycle gives rise to at most, which is 2 power the length of the cycle, upper bound on the length of the cycle, multiplied by m, and our choice of m was n squared, right? So I think there is a small typo here, so this is n squared, 2 power n minus 1 into n squared. So I may have to rewrite this a bit. So which just corresponds, so again n power n minus 1 can be upper bounded by 2 power n log n, right? You could just write n power n, which is 2 power n log n, and 2 power n minus 1 times n squared is nothing but n cubed minus n squared, right? So we have, which is 2 power n cubed plus n log n minus n squared. So you can notice that here we have n cubed, but then we have this n log n minus n squared. N log n minus n squared is a negative quantity. So this number is certainly less than 2 power n cubed, because n log n minus n squared is a negative quantity. So this means that the number of cycles of G prime is always less than 2 power n cubed. So the number of cycles of G prime is going to be at least 2 power n cubed if and only if G has a Hamiltonian cycle. So this means if we are able to count the number of cycles in a graph in polynomial time, we could solve the Hamiltonian cycle problem by this reduction, right? So this means this problem, if sharp cycle is in Fp, then P equal to Np, right? So right, this is what we have shown. Again, the idea is very simple. Every edge is replaced by this network. So if so the networks gives rise to a lot of options. So every cycle of a certain length k, it gets replaced by 2 power mk cycles in G prime. So if G has a Hamiltonian cycle, then we get 2 power n cube cycles in G prime, where we choose m to be n squared. Whereas if G does not have a Hamiltonian cycle, then the number of cycles that it gives rise to, even the biggest cycle, the n-1 length cycles gives rise to, even that will not reach the 2 power n cubed, because there is this exponentiation that is happening. So each additional length really takes it farther from the previous length. So even if you had a lot of cycles of length n into n-1, even then we cannot reach 2 power n cubed. This is the key idea of the proof. Okay, so finally we will define what is Sharpe completeness and then conclude. So Sharpe completeness is defined very similar to NP completeness and other things, but there is one small difference. So a function is Sharpe complete if that function is in Sharpe, right, which is the first step. F is in Sharpe, and all the G in Sharpe reduces to F. So till now we have used the menu one reductions, but here we will use the Turing reduction, which we saw while we defined the Oracle model. Right? We mentioned Turing reduction, especially while talking about Baker-Gill-Solovay theorem. Right? So if G has a function, so basically an FP machine with an Oracle access to F should be able to compute G. So if you can solve F, you can solve G, or if you can count F, you can count G as well. Right? So some examples. So two of the examples we have already seen. One is sharp sat. Basically, the key idea is we have seen the reduction. Right? Why is sat NP complete? Because you can look at the computation table. Look at the computation table or computation tableau. Phi is satisfiable. I have to explain a bit more. So you have to show that all the functions, all the NP machines reduce to satisfiability, right? So we can use something very similar to Cook-Levin theorem. So consider any Sharpe language. So the membership in Sharpe we have already seen, right? So consider G in Sharpe. Suppose NP machine G corresponds to number of accepting computations of an NP machine N. Okay, suppose G corresponds to the number of accepting computations of an NP machine N. So now look at the computation tableau of N. Look at the computation tableau of N, and the Cook-Levin reduction, right? The Cook-Levin reduction that we saw, actually this Cook-Levin reduction preserves the number of accepting computations. So what I am saying is that suppose Cook-Levin theorem reduction gives us some formula called phi n, right? So number of accepting computations of n is equal to number of satisfying assignments of phi n. So this is called, so this property where the number is preserved is called parsimonious. Okay, so this is a parsimonious reduction. So the number of accepting computations of n is equal to the number of satisfying assignments. So if you just think about the reduction that we did, it is not like we are merging multiple accepting computations of n into the same satisfying assignment for the formula. So this is a satisfying, this is a parsimonious reduction. Parsimonious means the number of accepting computations in the case of n is preserved when it translated to the Boolean formula. So because of which, if we can count the number of satisfying assignments of a Boolean formula, we can count the number of accepting computations of any non-deterministic Turing machine, which means any G in Sharpie can be computed, right? So any G in Sharpie can be computed with access to a SAT oracle, which is what we wanted to show. Similarly, other problems like tree coloring, clique. So tree coloring asks for the number of proper tree colorings of a graph. Clique asks for, so this is count the number of proper tree coloring, right, in G. So this is asking for count the number of k cliques where k is part of the input in G. So both of these are also Sharpie complete, right? Both are Sharpie complete. The easiest way to see that is by reviewing the reduction. Review the reduction from SAT to tree coloring and SAT to clique, and we will notice that the number of satisfying assignments of a given Boolean formula and the number of tree colorings are either same, or you can estimate one from the other. I think it is actually exactly the same in both these cases. We can notice that the number of satisfying assignments is equal to the number of proper tree colorings and k cliques. So if you can estimate 3 colorings or the number of 3 colorings or k clicks, you can also estimate the number of satisfying assignments. So these are Sharpie complete. Basically, if you can count the number of 3 colorings, you can count the number of satisfying assignments, and which is already shown to be Sharpie complete. Right. So these are some examples of Sharpie complete. I think most of the simple graph problems, even vertex cover, independent set, they're all Sharpie complete. In fact, what I said earlier, the number of bipartite matchings, even that is Sharpie complete. So we'll see the proof of that. This is a famous theorem. We'll see the proof of that also in the next lecture. So I'll just summarize. So we defined what is Sharpie, right? It's a complexity class that captures the power of counting, which corresponds to the number of accepting computations of a non-deterministic polynomial time Turing machine. We saw some examples like sharp SAT, sharp 3 coloring, sharp bipartite perfect matchings, and sharp spanning trees. These are all in Sharpie. Right? And we saw that Sharpie is at least as powerful as NP, and then the randomized complexity classes like RP, BPP, etc. We saw that counting the number of cycles, if we can do that in polynomial time, deterministic polynomial time, then P equal to NP. In other words, even though the decision version is easy in polynomial time, deterministic polynomial time, the counting version can become hard. Right? This was a very simple reduction where we replace edge with a gadget. And finally, we define Sharpie completeness, which means all the functions in Sharpie can reduce to the Sharpie complete language or Sharpie complete function. And the main thing is that we use Turing reduction. So we use Oracle access, so we could make multiple calls, unlike the many one reduction. And we saw that sharp SAT, sharp 3 coloring, and sharp 3 click are all Sharpie complete. So with that, I conclude today's lecture, lecture 49. And just to summarize what we have done in this week, we first saw that given a bipartite graph, outputting the number of bipartite perfect matchings is in RNC, right? Using isolation lemma, and you have a parallel algorithm to output the number of bipartite perfect matchings, right? This was the Mulmule-Vazirani-Vazirani's paper. Then we defined promise problems and Welian-Vazirani theorem, which says that even if we are given the promise that a given Boolean formula has either 0 or 1 satisfying assignments, even then with this promise also, the testing for satisfiability continues to be hard or is unlikely to be easy, right? And finally, we saw Sharpie. We defined and we saw some examples and defined Sharpie completeness. In the next week, we will see two important theorems. One that shows that the problem of counting the number of bipartite perfect matchings is Sharpie complete. It's also called the permanent. This problem is also called the permanent. And second, that Sharpie is very powerful, that in fact the entire polynomial hierarchy, it is as powerful as at least the entire polynomial hierarchy. So these two results we will see in the next week, and till then, thank you. Yeah.